Okay, today I'm going to talk about isometries. Sorry, I was delayed a little bit. Isometries, this is about the map between two surfaces, and those are the map preserves the length of the curves. And that means if you have a curve on the one surface, and which is send it to another surface, it does not change the length of the curve. And then this is called isometry. Okay, but I'm trying to change the definition, slightly definition. You know, there in the book they give the definition of isometry first, local isometry, then then prove the theorem which is equivalent to another condition. I'm going to use another condition because that's the traditional definition for the isometry. Okay. Okay. So I give a give a map, right? So from surface to another surface, our surface in three-dimensional space, okay? And this is a map, and then you know, at every point, it induce a linear map from tangent space to tangent space, okay? We also know that every, so this is the image space, okay? So this is the F of P. Okay, so let's take a look at the picture. This is our picture. Here's a point, S1. Here's another surface, FP. Okay, so S2. So you have a, then it induces a linear map from tangent space to tangent space. Okay, how do we define the linear map? Can we, yeah, let's try to recall the definition. Okay, the linear map is defined as follows. Okay, there are a couple ways to define. Okay, for any tangent vector, right, in the space. Okay, for any v in the tangent space, I'm going to define. So then you can choose a curve. Okay, so then there's a curve. Okay, on the surface. Okay, there's a curve on the surface such that v is going to be tangent vector to the curve. Okay, then there is a curve C over t on the surface such that it passes through the point, and the derivative is going to be a vector. Okay, then that curve is sent to a curve on S2. Then F circle CT is a curve on S2. Okay, and it is passing through the point FP, right? So the tangent vector, okay? So then F circle, this is tangent vector, is a tangent vector to the surface of the point, okay? So our definition of the linear map, there are a couple ways to define. This is one of them definition. This send V to, okay, F circle C, like this. Okay, that's a definition. Okay, so in other words, I can also write in this just using C prime T, right? It's going to be F circle C prime T. That's a definition. Okay, and you can also say that's independent choice of particular curve with the same direction. Okay, and the local formula, a tangent vector, right, can be, yeah, the tangent vector, yeah, let's find the local formula, okay? Find the form more, when we give a surface patch, okay? So let's find the formula, okay? This is a review for the linear, okay? So at the point P, you can have a surface patch. Okay, that's sigma. Okay, so that is a point, right? And it's a center to P. That's S1. So this is F. Okay, then you get a combination of the map, right? This is F circle sigma. So this is a, it's not necessarily surface match unless F is a local diffeomorphism. Okay, so this is also a surface patch for S2 if F is a local diffeomorphism. Otherwise, it is not going to be a surface patch. Right? But so nevertheless, you can always differentiate, right? So D, F, P send this tangent vector. This is a tangent vector, right? And to F circle this, right? From the above definition. And the FP sigma V, okay? You can easily see that. And so for any V, which is lambda sigma U, mu sigma V for the tangent in the tangent plane. So this is linear map. So it's going to be lambda, right? Okay. So this is also going to be F circle sigma U and plus me F circle sigma V. Okay. Yeah, this is usually ordinary differentiations because if sigma is, you know, is some open set in R2 to R3, right? And then the F circle sigma is also the map from R3 because F is a map, right? From S1 to S2, but both are in R3. So that's why the composite, you know, the composite of these two map, right? And then here's a sigma, right? From U, okay, to S1, then to S2. That should be the images, should be R3. So F circle sigma is going to be a map from U to R3 too, okay? So that's why you can use the ordinary differentiation to differentiate. So that is about the formula, okay? Linear, no, for a linear map, right? As long as you know the basis, right? The image of the map on the basis, then you can, yeah, then you completely determine the linear map. Okay, so actually this involves some Jacobian here. Well, you know how that. So when F is a regular map, right? Is that right? So whether this linear map is non-singular, invertible, and this can be determined by the so-called Jacobian, okay? The Jacobian. Okay, how do we define the Jacobian? Okay, for the Jacobian, you need two surface patches, one for S1 and one for S2. Okay, let's go further, okay? And this is S1, right? Let me draw the picture. Keep it right, draw the picture. Okay, this is this is sigma. Okay, and here that's U tilde, and here, and this is a P, that's FP, right? Okay, sigma tilde. Here's F. Okay. Okay, then you also have a map, right? This map, what I should call it, F circle sigma tilde. inverse, right? So you have a map from U to U tilde, and this gives you the so-called Jacobian. Okay. All right. So let's see. Okay. And I'm going to call it. We don't have any special name there. That's that is a let's call that f bar. Okay. So f bar is actually is a map not from S1 to S2, from U to U2. Okay. This is S1, S2. Okay. So take a look at this. Okay, df fp, right? Sigma u. It descends, right? It's going to be the differential. I think this one. Okay. But we can also express it in the following form. Right? So this is a function of f bar. Okay. So now my f tilde, right? So here's f bar uv is going to be u tilde v tilde. So u tilde v tilde is going to be the function of uv. Okay. So you get Jacobian with respect to you get a matrix we call Jacobian of f with respect to these two surface patches. Okay. Use a chain rule. Okay. This is going to be tilde. Right? Okay. Another one, the fp sigma v, and similarly, you have this. Okay. So that is going to be sigma u tilde. Okay. Now we can express it in the matrix form. Okay, it sends this basis to another basis. I'm going to use differentiate, right? So I'm going to write a matrix. The first one is going to be right here. Okay, so this is nothing. This is just the so-called the Jacobi. Okay, with respect to these two bases. Okay, so this dp is invertible if only if the Jacobian, the determinant is going to be this 2x2 matrix, right? This is linear algebra. If and only if the determinant of the Jacobian at that particular point is not going to be 0. Okay, this is the Jacobian. Okay. And so you can look at linear map using the matrix. Okay. All right. So now, all right. So now we are going to take a look at the first fundamental form. Okay. Okay. So by definition, okay, f from S1 to S2 is called a local and isometry. Okay, I'm trying to define slightly different from the book. Okay, I use the equivalent condition in the theorem. as a definition. I think it's much easier to do. If for any point S1, this P preserves the inner product on the tangent space. On the tangent plane. Okay, so because on the tangent plane, right, there is a naturally induced inner product here, because this is considered like a vector space in R3. So a vector, two vectors, you can talk about inner product. So how can I describe it? That means for any U and the V, okay, yeah. So don't be confused with the variables of the surface patch. Okay, I don't know whether we should use the same notation. Keep it, in the book it's easy to use a board. Okay, maybe yeah, that's better. Yeah, use the arrow. That means the vectors. So then you get DFP here, U bar, right, and then DFP So you have two vectors here, two vectors. You want to compare, right? You want to make sure the inner product of those two vectors, yeah, we call it dot product, should be the same as this. Okay, this is a very special map. Okay, so if a linear map preserve the inner product, immediately you can show that this is a invertible linear map. Okay, and so this is our assumption, right? This is our assumption. So it's a nice. So for local isometry, what you can get, okay? First, yeah, conclusion, okay? So here's a for local isometry, okay? What you can get? F. First, okay? It preserves the length, okay? The length of any vector. And that just because the inner product, you let U to V, right? Okay, that's a very important property. Then just because of that, then this implies it preserves the length of a curve. Okay, how to prove that? Well, you can show that, right? Let C of t be a curve on S1, okay, on surfaces. Okay, and those, you have two surfaces here, right? So let's draw the picture, okay? That's S1, that's S2. So take a curve C of t here, and then you get an image. It's also on it's a curve on the S2, right? So although that look different, they have the same length. That's what I want to say. Okay, let's see why. Okay, by definition. Oops. Okay. So by definition, the length, let's look at the length, right? The length of a C. Okay, I call this is C. and that's the image of C, right? So the length of C is going to be integral of, right? Okay. Right. So first of all, now, then the length of F circle C is going to be also the integral. This is going to be F circle C prime T dt, right? So we want to show that thing, but this derivative is nothing but F of C prime T from our formula, right? So the length right? Because it's preserved, right? This is based on what we have here, right? It's the same identity. So this is going to be C prime T, right? Therefore, they have the same length. Right? Another important thing, I think, for local isometry, F must be a local diffeomorphism. Okay. The reason is, okay, this is a local isometry, just a smooth map, right? The reason is as follows. DFP is a linear map, right? This linear map preserve the inner product, even the norm, right? Preserve the inner product. Yeah, if it preserves the inner product from linear algebra, you can show that, there's the inner product here, right? And also inner product here, this is FP, right? There is an inner product in the tangent plane. So it's two-dimensional vector space. If some linear map preserves inner product, then this must be invertible. Okay, as invertible means by the implicit function theorem, then it is a local diffeomorphism. Okay, then F is a local. That's invertible for every point for any P on S1. So this is a local diffeomorphism. This is by the inverse function theorem. Okay, called inverse function theorem. Okay. A linear map, if it preserves the inner product, why it's invertible? Why the Jacobian cannot be zero? If the Jacobian is zero, then clearly you have a zero eigenvalue, and that zero eigenvalue send a non-zero vector to a zero vector. That's impossible because the non-zero vector has a length, positive length, and the image is zero, right? So that's why that's impossible, right? Because it preserves the length of the vector. Okay, so that's why this must be singular, invertible. Okay, non-singular, yeah. All right. So That's why local assumption must be local diffeomorphism. Okay, and then and conversely, if you conversely for the first part, conversely, if it preserves the length of the curve, and I think this is also and I assume to preserve the tangent vectors. Okay, so this is I think this is easy to prove. Okay, so let's an exercise. Okay, show that suppose f, okay, preserve the lengths of curves, okay, S1, okay, then f is a local isometry. That means it preserves tangent vectors. Isometry, i.e., DFP by my definition, okay, okay, for any u, v in the tangent plane, tangent space, tangent plane. Yeah. Okay, that's the inner product. It's the dot product, the inner product. In physics, we use a dot product. In mathematics, we call it inner product. Dot product only works for vectors in three-dimensional space. Okay. All right. How do I do that? How can I prove? Okay. Proof. It's very simple. Okay. For any vector, okay, I take a curve such that the tangent vector is v. Okay. So you can take a curve. So there is a curve C S1 such that it's going to be the point P and C prime is going to be V. Okay. So you can always, yeah, you can always find the curve passing through that. So the tangent vector is going to be the given V. Okay. Then the length. Okay, I'm just talking about the length, this piece, right? So the integral from 0 to t, okay, the length f, and I can put an epsilon, okay, small epsilon, okay. So c prime t dt, that is the length of a small piece, okay. This length should be equal to the length of the image. Okay, because it preserves the length of curve. Okay, but this is nothing but df c prime t. Okay, now so far it's okay, right? So what is the next step? Next step is divide by epsilon both sides. Okay, then you let epsilon goes to 0 from positive side. So the left hand side is c prime. The left hand side, okay. That's it. So df, yeah, that's point P. Okay, dfp preserves the norms defined by the inner product. But of course, preserve the inner product. That's if some linear map preserves a norm, and it must be, that's from linear algebra, okay? Must preserve the inner product, okay? So that means this is always true for the tangent vector at point P. Okay. A linear map preserves the length of the vector. You can show that it preserves the inner product. Okay. Because then the inner product can express as just think about how do you solve this problem, right? Yeah, you can look at this. Okay. This is the inner product. Okay, minus and plus twice, right? And okay, so if you take a subtraction and divide by 2, no, divide by 4. Right? So if a map preserves the length, then it preserves the inner product because inner product can be expressed as a difference of the two lengths of the two different vectors. Okay. So using that, you can show that okay. Okay, right, by the definition, by the above formula. Okay, I'm going to put u plus v here because it's linear. Right? Then right? Then that's just that. Okay, so the inner product is preserved. That's it. So now what we can say, and this is the equivalent, right? We define a map to be local isometry if it preserves a length of preserve inner product of tangent vectors. Then you can show that it must preserve the length of the curves. But conversely, if it preserves the length of curves, then it also preserves the inner product of the tangent vectors. But the concept, yeah, but it also implies that in any of these two conditions, it also implies that F is a localized diffeomorphism because the linear map DFP is invertible. Okay. Right. So now let's take a look at the first fundamental form. First fundamental form was respect to, and if you remember, right, the first fundamental form of the surface is defined by the inner product. Okay, roughly speaking, the inner product is just first fundamental form. Okay, the first fundamental form is actually the inner product on the tangent space. Okay. The first fundamental form is S at the point P. The first fundamental form, okay, IP and V, tangent vector V, right, is defined to be the inner product, right, of the vector itself. So it's quadratic form, right? And then if you have a surface patch, sigma, right? And then V is going to be lambda sigma u. mu sigma v. Okay. Then you put that, and you will get the inner product, right? You will get lambda square E plus 2 F lambda mu plus G mu square. Okay. So E is going to be sigma U dot sigma U. F is a sigma U dot sigma V. And G is a sigma V dot sigma V, right? So that's another another form using local code, using surface patch, okay? Okay. Now, what I want to say, then you have two surfaces, right? You have two surfaces, okay? That's S1, F, S2, okay? We suppose that F is a local isometry. So it is local diffeomorphism, okay? So it is a local diffeomorphism. And then we have, right? Then we have what? Then the second fundamental form is the same, okay? So we have the second fundamental form, V is going to be FP and the DFPV, okay? From the definition of the isometry, right? So what does it mean here? This is a V dot V, and this is a DFP, okay? So because it preserves the inner product, of course it preserves the length or the square of the length, right? Okay. So you can use the second fundamental form, no, the first fundamental form, sorry, first fundamental form to to define local isometry. Okay. Now you use a chart. Yeah, look at surface chart. Using surface chart. Okay. So now using the surface chart. Okay. Sigma. Okay. For surface patch, not chart. It's sometimes called chart. Okay. Surface patch sigma. Okay. For S1. Okay. F sigma is also surface patch. Okay, that is a surface patch. Is a surface patch for S2. The reason is F is a local diffeomorphism, right? So it's so when U is small enough, this becomes a one-to-one map. All right. So so I'm using above identity, right? Using the above identity, what do you get? Okay, using the above identity. Using the above identity, let's find out yeah, that's my sigma field, okay? All right, for V, lambda sigma U, mu sigma V, okay? So then D, FP, here, right? It's going to be lambda sigma U tilde, mu sigma U tilde. Okay, so V dot V is going to be lambda E, right? 2 F lambda mu G mu square, right? So DFPV dot DFPV, and use this one. So it's going to be E tilde lambda square plus 2 F tilde lambda mu plus G tilde mu square, right? Right? Yeah. So for example, here E equals sigma U dot sigma U, and this E tilde is a sigma U tilde dot sigma U tilde. Okay. So they're equal. Equal means these two quadratic formula equal. So equal means, yeah, okay. Okay, for any V in the tangent plane, if and only if E equals E tilde, F equals F tilde, G equals G tilde. All the coefficients are the same. Those are the coefficients with respect to the chart surface patch F circle sigma. This is with respect to sigma. This is sigma tilde. Okay, right. You know, when you're talking about EFG for the first fundamental form, you have to mention which surface patch you use. Okay, right now both the surface patch are from U to R3, but the one image is S1, other one the image is S2. Right. So we have to, we should take a look at the picture. Take a look at some examples. Example. Let gamma U be a curve in R3. Okay. With curvature KU. Okay. And where U is a arc length. Okay. So that means gamma prime U is always equal 1. Okay. And that is given. Okay. But we know that this is not a for given curvature. Okay, gamma is not uniquely determined. Okay. Okay, I can also let gamma tilde you be a curve in R2. Okay, with the same curvature KU. And that can be done, right? So this is not part. Yeah, this. I think this is always a positive function, and not. Oops. Yeah, we always assume it's positive function. Right. So how do you get a curvature, right? The curvature is going to be the length of I think the second derivative, right? That's our definition of the curvature. That's why it's going to be positive. That's possible. Yeah, the torsion, I can assume that the torsion not equal to 0. Okay. Once you give a torsion, an arbitrary function, non-zero function, you can almost uniquely determine curve. So here, it's going to be like that, right? And here, I use a plane. Here's in three-dimensional space. So this is a curve, gamma 2. Okay, this is a gamma in three-dimensional space, x, y, z. Okay. So both have the same curvature function. That can be done. Okay. So what I'm going to do here is I'm going to construct a surface. All I have to do is find the surface patch. Okay, find the surface patch. It's a U and a V. I'm going to only consider positive V. Okay, so I consider this, send it to here. So sigma U V equals gamma U plus V gamma prime. Okay, so if V is we only consider positive V. Okay, so that means this is a tangent vector, right? So it goes like that. Now it's harder to draw it. They're all tangent vectors. Tangent line, sorry, tangent line. Okay, so it's, you can imagine what kind of surface you can get. Starting from the origin, but does not include the curve. It does not include the point of curve, right? All right, and here, because the plane curve looks like that. So this surface, this sigma 2 dot UV equals sigma U plus V sigma U prime U. I think of V is positive. This is the image is going to be is plane. Okay, okay. The image is plane. Okay, so let's compute both sides. It's the same thing, right? It's a sigma U okay, which is gamma prime U plus V curvature U and the normal vector U, right? And this will be the curve tangent vector. So I'm going to change it to T. Right? Sigma V is just gamma V, gamma U prime, which is TU, right? The tangent vector. Right. So now what do you get? E is going to be 1 plus V squared KU squared, right? F, I think F is 1. The inner product is 2. G is also going to be 1. Okay. Right, so now on the other side, okay, I also have a surface patch. So sigma 2 dot U is gamma U prime U, right? Plus V. Okay, similarly, you get T 2 dot U plus VKU, the normal vector, right? And sigma V, this is just equal to T 2 dot U, okay? So you will get E2 dot is going to be 1 plus V squared KU squared. F2 dot is going to be 1. G2 dot is also going to be 1. And you see that the coefficients are identical. Okay? Yeah. They are identical. Now, what does that mean? I'm going to define the map. I can define the map from S1 to S2. Okay, so the map for the point gamma u plus phi gamma prime u is a sender to, that's my point P. So sender f of P. Fp is gamma tilde u plus phi gamma tilde u. Okay, you can define that, right? I'm just very precise. Okay, so you get a map. Okay, you get a map. So the surface of this portion of the surface, okay, is assigned to this portion of surface. Okay, so this point is assigned to this point, but this is a flat. This is a portion of the plane. This is on plane. This is in the space in R3, right? On plane R2, right? And yeah, there's isomorphism here. Right? So this point is assigned to that point, it's F. Okay. So in other words, if this is a map sigma tilde, this map sigma, right? I think sigma, yeah, by the definition, sigma tilde UV is just F circle sigma U. Okay. Yeah, okay. So what that tells you, they have the same first fundamental form. Okay. So this is S1, that's S2. S1, S2 have the same first fundamental form, right, with respect to sigma and sigma tilde. Okay, so that means F is an assumption. Actually, I say it's local. Actually, this is a diffeomorphism. Is an assumption. Okay, so we get an assumption from the curved space to a flat space. That's weird, right? This kind of map is very important. Okay, so in mathematics, you can construct an interesting. This is a curved surface, right? Curved surface. Whatever you see, you have a movie here, a picture, and you get a picture, a flat picture here. It's not curved. Okay, in R2, it's a flat, right? The image is flat, and here it's curved, twist. Okay. Yeah, there's so many interesting diffeomorphisms. Okay. So if yeah, it's hard to draw how does the picture. Okay. For example, yeah, if we have something here, yeah, this is interesting. If we have something here, and then you will get something here. But when it's a flat, complete flat, this is a curve in the space. But you can find the map. It's called isometry. Okay. And any curve on this surface, send it to a curve in the plane. And this map preserves, it's hard to imagine, right? Preserves the length of the curves. Okay. So F preserves the length of curves. Okay. Also preserves the angles between two vectors, okay, because it's preserved inner product. Inner product determines the angle between two vectors. Okay. Yeah, note, uh, and local isometry preserves the inner product, also preserves, then that implies preserves the length and preserves the angle between two vectors. I did not mention that. Okay. Yeah, inner product, isometry, and isometry. For an isometry, okay, this preserves the inner product, right? Okay. But this also implies two things. One, it preserves the length. Come on, yeah. It's you. All right. But also, you can show that it preserves the angle. Okay, it preserves the angle between DFPU and DFPV is the same as the angle between U and V. Okay. But since our norm is come from the inner product, so these two they actually is equivalent. Okay, but that is a weak condition. Okay, so I mean I already showed that the preserves the norm if only for the inner product. Those are two equivalent, but it proves the angle does not mean it preserves the length. Okay, so there's an important class. Yeah, the angle. How do you define the angle? Angle is that cosine theta equals okay. That's the definition of the angle. Right, given two vectors, u and v, the angle is determined by this. It's the inner product and also the length of these two vectors. Okay. All right, so I'm going to introduce another definition. And this is a section actually 6.3. Okay. A map from S1 to S2 is called a conformal map. Okay. Conformal map, or whatever is the name. I think it's called conformal. Let's see, what's the name? Conformal mapping. So conformal mapping. So that's it. Conformal map if it preserve the angles. Okay. So you have two angles here. This is theta, and this is u, and the v. It's in the tangent plane, and then have a DFP u, and this is a vector. It could be very long, could be very short. I know, but the angle is still the same angle. All right. The last example I show you, a curved surface can be mapped to a flat a piece of surface in R2, a flat plane, but not every surface can be mapped to locally, at least mapped to a piece on the plane. Okay. Not every surface. Okay. So that's why we have to lose a condition. We want to assume. We do not assume it preserves the length of the tangent vector. The vector can be shorter, can be longer. Okay. I just want to preserve the angle. Okay. This is called conformal maps. Okay. Okay. That was a very important theorem, which is actually is proved by some mathematician. Not to have a lot of applications in imaging process. Actually, if we study computer science in imaging. Okay, so I just want to mention that theorem, but we're going to probably not every we cannot prove that. Okay, so the theorem says that every surface in R3 can be we call it conformally diffeomorphic to surface in R2. Now, what does that mean? So you have a surface here, and then you can always local piece can be sent to here, but then it does not preserve the distance between 2 points, and there's a standard way to construct such map. Okay, but then it preserves the angle. So if a two tangent vector, then the angle theta, and then you have two tangent vector, the angle between two images will be still the same. But the distance between 2 points are not preserved. Okay, this kind of map is very useful. Okay, right now it's adopted to medical science. Think about that. If you get an MRI scan on the cortical surface of your brain, right? And how do you see the cortical surface? How it is changed? So based on mathematician's theorem, one can design procedure, program. So I have to work with computer scientists together. So you can always project it to the screen. Screen is a flat screen, it's not 3D screen. So the doctor can see how the change of your cortical surface. Suppose you have a tumor growing in the brain, so the cortical surface changes, deformed day by day, right? So you don't need to open the brain to see that. CT scan, yes, you can get some information, but not 100% information can get. So using this mathematics, now one can design a machine kind of scan. Okay, so you can scan your brain without surgery, then you can project on the screen, then you can see the change. But you have to understand the distance between 2 points on the cortical surface in the image on the plane. It's not exactly the same distance. Okay, but it's good enough to tell how changes of the surface, cortical surface, when the tumor is growing. Okay, so that's why I just want mention this is a very geometry is where we can use it. Okay. We live in three-dimensional space. At least we should understand three-dimensional surface in three-dimensional space. Okay. Now, general relativity theory you heard about, right? It's about the geometry of three-dimensional space, a three-dimensional surface. We still call surface, okay, but three-dimensional. but it's hard to imagine because our body is embedded in this dimensional surface. Okay, it's a curved maybe, it's a surface, but it's hard to imagine. Okay, that's why very few people understand Einstein's theory, general relativity theory. He's talking about four-dimensional space because time is another dimension. But when the time changes, this three-dimensional space, which is our physical space, changes, and it's also curved. Yeah, right. But it's hard to tell because you are inside the three-dimensional curved space, just like an ant. Ant climb on the surface. Probably an ant cannot tell the surface is curved because the ant, it can only see local area, okay? And then it's always flat to the ant if the surface is large enough. It's two-dimensional, right? Because it's imaginary, okay? So it's hard to tell whether the surface is curved for the ant, okay? So our human being have the same problem here, and yeah. All right, so first of all, we have to say that how it preserves the angle, a linear map, okay? So it's a one can show that. I probably don't have a time to prove, okay? Okay, so for a linear map, and that's what I want to talk about, okay? So this is a map, right? From tangent space to, okay? So suppose, yeah, we don't need to suppose. Okay, so F, yeah, it preserves angles between tangent vectors if and only if right? If and only if this is the inner product is going to be proportional to some number, right? For any u and v, right? Now, if this is true, it's easy to see why is you get the same angle. Okay, lambda p is not equal to 0. Okay, proof. I only can prove this easy part, but this linear algebra. Okay, linear algebra. Okay, so if that is true, right? Then what are you gonna do? This implies at least they let u to be v, right? At least. So you can get at square lambda p, right? Because let the v to be used and both sides is the square of the length. Okay, so the angle cosine theta, the angle, right? Between between two images, right? Right. Right. So by definition, this is FP, right? By the about equation, and this is a square of p, and this is a square of lambda p, right? And clearly lambda p is going to be canceled out, right? And that's the angle between u and the v. So that's why the angle is preserved, right? That is why the angle is preserved. Okay. Yeah, if you want to look at the picture, this is the angle between theta, and now U and the V, and that is the angle, and DFPU, and I call this theta, right? DFPV, and that becomes theta, right? And compute it, and this is the cosine theta, so that implies theta equals theta, right? So that's why they have the same angle. All right, and for linear algebra, from linear algebra, if it preserves the angles, I'm pretty sure one can show that the inner product has the relationship, right? Yeah, it's a little bit tricky here to prove, but I don't have a time. Okay, so I stop here. Yeah, you can think about how to prove the other side. Okay, a linear map, if you preserve inner product, preserves the angles, can you prove it did not preserve inner, the inner product is going to be proportional to each other.